This is a lesson to be used in a flipped classroom setting. It's a lesson about evolution and some of the odd phenomena that show up in nature as a result of evolution and its randomness. We're going to be looking at the blind spot in the human eyeball. It's a feature of both eyes, the part of the actual anatomy that's there as a result of the randomness and the way the eye evolved. And it's not just humans, it's all vertebrates that have this kind of odd setup. So this lesson is about why you can't see as well as you think you can. Or another way to think of it is why things don't always work as well as they could. So we've already covered survival of the fittest and natural selection and the basics of how natural selection works and leads to evolutionary change over gradual periods of time. But just a quick review of the word competition. When we say competition, who is it that is competing with whom? Do we mean one species competing with another species? This quick illustration helps to show kind of what we mean by competition. Two men are walking through a forest. Suddenly they see a tiger off in the distance, running toward them. They turn and start running away, but then one of them stops, takes some running shoes from his bag, and starts putting them on. "What are you doing?" says the other man. "Do you really think some sneakers will help you run faster than the tiger?" "I don't have to run faster than the tiger," he says. "I just have to run faster than you." So it's not one species competing with another. It's not the tiger competing with humans or humans competing with tigers. When we say competition, we mean one species competing with itself, different members of the same species competing for the same types of resources. One feature of natural selection is that it happens in very, very gradual incremental steps, and each step along the way must be beneficial. So you might ask, how do you get from no wings to a fully developed wing that you see in a bird? What purpose does the in-between stage, what purpose does a partial wing serve? Can that be useful or beneficial for survival? There are chickens that live in Key West, Florida, that were introduced there years ago, and these chickens spend a lot of their time up in trees to get away from the feral cats that otherwise would chase them away. So what's going to happen to this chicken if she falls out of the tree? She doesn't have a fully developed wing, so she's not going to be able to fly away, but all right, so she fell. That didn't really illustrate it all that well, but normally the chicken is not going to fall to its death. They have wings, they flap around, and they manage to make it to the ground pretty safely. So again, each step along the way in natural selection must be beneficial. Evolution doesn't look ahead and imagine the future in which a fully developed wing is going to help you fly. Even a partially developed wing on its way to becoming a fully developed wing needs to be beneficial. So sometimes if you can't think of the benefit and how it can help you survive, it's just a matter of a failure of imagination. Take a look at this bird trying to run up a steep incline. Having a partially developed wing might not help it to actually fly, but it's going to still help it to save its life if it's trying to get away from this cat. So obviously feathers are useful for flight, but feathers actually predate birds. If we go back further and further in time, we get to the dinosaur family tree. And many of you probably already know that birds are the one group of dinosaurs that did not go extinct 65 million years ago. It's pretty well attested in the fossil record that many of the theropod dinosaurs, including Archaeopteryx, these guys down here, had feathers, as shown in the fossil record, but as we go further and further back in time, we're starting to realize that a lot of these other more primitive dinosaurs also had tiny little downy feathers, showing that the feathers were something that evolved long before anything resembling a wing. So this is a great example of one adaptation useful for one thing that was then later hijacked for a completely different use, in this case, the modern wing of birds. So here's an example of a pretty primitive dinosaur going back 125 million years, long before anything resembling a bird. And as you can see, we have these big, long, thin, wispy feathers all over its tail in this really well-preserved fossil. The fact that these feathers are there at all shows that obviously they must have been useful for something, possibly bright colored feathers that were useful for attracting a mate, but definitely not for flight. So now we're going to talk a little bit about some of the odd design features in some of the specimens we find in the animal kingdom, starting with the giraffe. This is something called the recurrent laryngeal nerve, and it's a very oddly designed feature in the giraffe and really many animals. This is something that connects the larynx, which is in the voice box region of the throat, to the brain, which, as you can see here, is just a few inches away. So if you're going to connect the two with the nerve, you think you'd only need a nerve that's only a few inches long. It's only connecting those two things, but it turns out the nerve goes all the way down to the bottom of the neck, around the aorta, and back up into the throat. So obviously this is a very odd design. Why would you design a neck that has a nerve that wraps all the way around the heart for no apparent reason? It's taking pretty much the longest possible route to get from point A to point B. So the design of this nerve seems to defy all logic unless you think in terms of evolution. So what is the explanation? If we look at humans, we see that we have a similar odd setup where we have a long nerve, much longer than it needs to be, connect these 2 points. And again, it loops around the aorta for no apparent reason in here. So what ancestor do all tetrapods share? Tetrapods would be mammals, reptiles, amphibians. If we go back far enough, we get to the fish. And in the fish, you can see that the brain and the area corresponding to the modern larynx is just a straight shot. It's this tiny little nerve that only goes a few inches, but it does loop around this particular part of a blood vessel that corresponds to our aorta. So from that starting point, all the descendants of fish were basically stuck with that weird design. So this odd setup is not a result of being any sort of good design. It's just there because our ancestors had it, and so we're stuck with the same setup. It's survival of the good enough to make it. If we extend this same principle to some of the longest necked creatures ever on Earth, the sauropod dinosaurs, this laryngeal nerve, which must have been there even though it doesn't fossilize, would have been almost 100 feet long just to go a couple inches from the brain to the larynx. So evolution cannot see into the future. It has to work with whatever is there, whatever works. So the human eye is an example of a highly complex organ that people like to cite as evidence of the fantastic design of the human body. And here's a quote from Darwin explaining what he thinks about the eye, taken from The Origin of Species. To suppose that the eye, with all its inimitable contrivances for adjusting the focus to different distances, for admitting different amounts of light, and for the correction of spherical and chromatic aberration, could have been formed by natural selection, seems, I freely confess, absurd in the highest possible degree. Creationists like to take this quote and use it to justify their so-called evidence that Darwin didn't have an explanation for the eye and thought that the eye could not have evolved by natural processes, almost like it's disproof of his own theory. But usually when they quote this, they tend to leave out the next part, which is this. Yet reason tells me that if numerous gradations from a perfect and complex eye to one very imperfect and simple, each grade being useful to its possessor, can be shown to exist, if further the eye does vary ever so slightly and the variations be inherited, which is certainly the case, and if any variation or modification in the organ be ever useful to an animal under changing conditions of life, then the difficulty of believing that a perfect and complex eye could be formed by natural selection, though insuperable by our imagination, can hardly be considered real. In other words, he's saying that even though it seems absurd or crazy to think that something so complex as the eyeball would have evolved by natural processes, reason tells Darwin that it must have happened. Creationists like to cite an idea called irreducible complexity, which means that certain organs are so perfect and so well designed that they had to have some sort of intelligent creator for them to work the way they do. In other words, natural selection is not enough to explain their structure and function. So is the human eye an example of this? Is it irreducibly complex? In other words, could it function at all if every single part wasn't present in its current form? A good example to refute that is someone who has cataracts. Obviously, someone with cataracts has cloudy covering in their cornea from mineral buildup, and it doesn't prevent them from seeing. They can't see as well as someone with a fully functioning eye, but they can see better than someone who has no eye at all. In other words, it's an improvement. It's a feature that would help them survive compared to someone who doesn't have an eye at all. So I'd really encourage you to check out this video on the evolution of the eye featuring evolutionary biologist Richard Dawkins. The link here is not going to work, but I'll put the link in the video description for you to check out. So the basic idea of the video is that if we look in nature, we can see all sorts of intermediate stages of eye development, starting with the euglena, which is a single-celled protist that just kind of has a flat disc of pigment cells that are able to sense light. If we go to something a little bit more complex, we get to the planarian worm, which has kind of a C-shaped or cup-shaped arrangement of cells, which is able to sense which direction the light is coming from. We go to something a little bit more complex yet again, we get to the chamber nautilus, which has a similar arrangement, but it's closed over on itself, leaving just a tiny little opening filled with water for light to pass through. This acts as a pretty sophisticated eye, but it's not able to really focus into an image. If we look at the sea snail, we see something that's closed over on itself completely, along with a refractive lens made of just jelly that's able to actually create a pretty clear image. And finally, we get to the most complex, and we see the octopus eye, which has a fully formed lens that's able to kind of move in and out to focus an image that's just as clear as the image that we see. So the basic idea here is that for natural selection to work, there always has to be a gradual progression in which each tiny step is somehow beneficial. Any detrimental changes will get weeded out along the way, but beneficial changes will accumulate a little bit at a time until the resulting trait is much more complex than what it started with. And natural selection is perfectly capable of explaining something as complex as the human eye. So here's where the demonstration of the blind spot in the human eye comes in. For this demonstration, all you need is a piece of paper. It could be a random scrap paper. In this case, I'm going to use a piece of paper in my notebook. And all you need is that and something to write with. So now you're going to take your piece of paper and you're going to draw 2 dots on the paper. I'm going to use this Sharpie so you can see it really clearly. I'm going to draw 2 dots. Each dot should be about the size of your fingernail, and they should be about the same distance apart as your index finger and your pinky if you hold them up like this. You want them to be perfectly horizontal on the page. Now listen carefully. For this to work, you need to follow the instructions just right. I'm going to flip back a little bit so you can see what I'm doing. I am going to start by closing my left eye, and while I do, I'm going to hold this paper horizontally so I can see both dots, but I'm going to stare with my right eye only at the left dot. And I'm going to start with the paper very close to my face, but now I'm going to slowly move the paper back. I'm going to continue just looking at the left dot, my right eye focused on that dot, pull it back until I get to right about there. And when I get there, this dot is completely gone. I'm staring at this dot, and at this point in my vision, I can see nothing. It basically just looks like lines continuing through the page. If I go a little further, right about there, now it reappears, and I can see both dots once again. So again, the way it works is I'm using my right eye, I'm closing my left eye, I'm staring just at the left dot, and as I move this away, still staring at this dot, this is the one that completely disappears and goes blank. You could do it the other way too. If I close my right eye, I can start by looking at the right dot with my left eye, and the same thing will happen if I move the paper to about here. Now I only see one dot, the other one's completely gone. If I look back over it, I can see both dots, but if I stare at this one, the left-hand dot is completely gone. So make sure to try it out for yourself a few times until you get it, because the effect is pretty amazing. It's one of those things where you have no idea that you have this blind spot in your vision until you put an object directly in it. And then you can see that there's one spot where you literally cannot see anything. So why do we have this blind spot? It's obviously not something that helps us to see better. It's something that we see pretty well despite the fact that we had this blind spot, and we don't even really notice it because our brain kind of does a pretty good job of blurring it out and covering it up. So look at the design of the eye, and we can see that we have light basically passing through the hole in front of your eye, the pupil. It comes back and hits the retina. This is where all those light sensitive cells are. But if you look at the retina, you can see that all these cells must be connected somehow to the operating system, which is your brain. So here's your brain over here, not to scale, and a terrible shape. But if we look at this point right here, we can see this is where the optic nerve connects to your retina. And at this particular spot, there are no light-sensitive cells because that is where the connection point is between your brain and your eyeball itself. So just like the kind of odd design in the neck of a giraffe and this long, long laryngeal nerve, in the human eye we have this kind of odd feature that only makes sense if we think about the fact that the eye evolved from a beginning point in the earliest vertebrate eye. And so the design that worked then is the design that we're stuck with. If you were to design an eye, you wouldn't design an eye with a blind spot in it, but that's the way our eye is set up, and that's the way it's been for 500 million years or so. This may not seem like such an odd design feature of the human eye until you compare our eye to that of invertebrates like the octopus. You can see our retina here has a network of nerves that actually connects to the front of these cells, which means the optic nerve gets in the way and creates this blind spot. If we compare that to the octopus eye, we have a design that makes much more sense. We have an optic nerve that actually connects to the back of the retina. So our design is kind of like having a TV where all the cords are plugged directly into the screen, partially blocking out the picture, so that the image that we see is not quite as clear and defined as it could be if you were an octopus. If you were to design an eyeball from scratch, the octopus eye is a design that makes much more sense. But the human eye is a result of just millions and millions of years of evolution from a common ancestor that started with a setup that worked well enough for it and has been modified over the millennia into the eye that we know today.